It's a pleasure to welcome today's seminar speaker, Enrico Calzavarini, and a special welcome to his colleagues, our other guests. Enrico started out with a PhD in Italy, in the University of Ferrara. I got it right? And then he went on to do a postdoc in the Netherlands with Detlef Losse, whom you all know, and then, or know of. And then he did another postdoctoral stint in École Normale Supérieure in Lyon before joining the University of Lille as a faculty member. So we look forward to his talk. Enrico.
Thank you. Thank you, Rama, for the invitation. So the title of my talk would be Exploring Turbulence Through Particle, Statistical Property of Spheroids in Turbulent Flows. Before beginning, let me say 2 words about where I come from. So I and Sylvia come from this city, Lille, which is in the top north of France. It's a city which is well connected to the rest of Europe. In 1 hour, you can go to London, Paris, Brussels is half an hour. So it's very well. No, by train, by train. Oh. By train, yes, you leave in the morning at 8 and you are in London at 8:15 because you take advantage of the change of time zone. Yes. So it's very convenient to move from there. The university is a medium university in France, so it has 70,000 students, 1,100 PhD. I got this from the website. This is our lab, the building where there is our lab, and we are a small units in mechanical engineering, formed by where there are 20 faculty. We are all teacher and researcher. A variable number of PhD, usually around 12, and 2 teams. We work in solid and fluid mechanics, mostly in numerics, but there are theoretician and experimentalist activities too. Then concerning my research, so as Rama mentioned, I did several postdoc after my thesis, so I had the occasion to work on different fields. I started working on Rayleigh-Bénard convection, on numerical simulation of convective flows. And then I moved gradually to study the statistical properties of turbulent flow from the Eulerian point of view, initially, in relation also to what we saw in the Rayleigh-Bénard system, and later on the Lagrangian properties. This research was boosted by the fact that at that time there were experiments available, and so I moved to particles and bubbles transported by turbulent flows. And then I played a lot in this area of exploring this wide parameter space, which is constituted by density, size of the particle, shape of the particle. So this was pretty much up to, till my postdoc in Lyon. Then when I arrived in Lille, I started to interact with a laboratory which is on the coast, where they are interested in plankton. They have in particular zooplankton organisms, which are called copepods. And so we started a collaboration in trying to model as active particles these organisms. And more recently, I dedicate myself, and also in collaboration with Sylvia, to the activity of understanding how convection, and in particular turbulent convection, interacts with a melting boundary. And this in relation to problems of ice melting, so geophysical application, and ice, and the opposite, also ice solidifications. In more recent times, I try to combine my 2 topics of activity, so convection and particle, to study sedimentations in convective system, in particular in relation to geophysical problem, such as, for instance, solidification of magma oceans, in which you can have a fractional crystallization, so small crystals which fall down. And I did all this activity basically here, so numerically, but I loved to interact with the experimental group, and this will emerge also from my talk. So talk outline. I will present an overview of a series of work which concerned some statistical properties of particle in a turbulent flow. And in particular, I will recap initially what are the models that we use, what are the main simulation results which obtain numerically and in the experiments. And I will try to highlight what for me were interesting questions when I started this work. And I will present some new results which concern the study of large non-spherical particles in a turbulent flow. In particular, I will focus on acceleration statistics and rotation statistics. And I will give some perspective. So let's start. You know that if a particle is very small, so small that its inertia can be neglected, so it's the equation which describes its movement of center of mass is the one of a fluid tracers. It looks simple when we write in this form, but this hides the fact that there is Navier-Stokes hidden somewhere here. In fact, if you are interested to the acceleration, the Lagrangian acceleration is the right-hand side of the Navier-Stokes equation. And this, despite its simplicity, it gives rise to a complex phenomenology. And here I put one of these vortex filaments which constitute turbulence. And this is a trajectory of a Lagrangian particle which is spiraling into one of these vortex filaments. As soon as inertia is not negligible, as you know, there is an equation that we know under the name of Maxi-Riley-Gatignol equation, but in fact is an equation which collects many terms and which is the result of the contribution of many authors. So Stokes contributed to the calculation of the drag term, Boussinesq, Basset, Ozine to the history force. Later, Chen and Corsin-Lumley tried to model the pressure gradient term, or the fluid acceleration term, and the reformulation of this equation and derivation was given in the 80s by these two articles that we often cite. This equation, so it contains many hydrodynamic force, drag, added mass, fluid acceleration, history, and buoyancy. It is accurate as long as the Reynolds number of the particle, the Reynolds number of the particle and the Reynolds number based on the shear scale of the flow are small. If this is not true, the situation becomes much more complex and less clear. So if, for instance, the shear Reynolds number is not vanishing, we should consider Faxen correction. So if the scale of the particle is large or it is comparable to the scale of the typical gradient in the flow, essentially there is this non-correction which consists in substituting to the velocity its surface average in the drag and in the history force, in the surface related force, and substituting the velocity with its volume average in the fluid acceleration and in the added mass term. This is a correction for Reynolds, shear Reynolds number finite. When the particle Reynolds number is finite, there are empirical corrections suggested a long time ago by Schiller and Neumann. The drag increase, and so we have to add this dependence which grows with the Reynolds number. There is more drag on a particle. It's an empirical correction. And another correction that we should consider, and which is particularly important for particles which are lighter than the fluid, is the lift force. This is the lift force in the form given by Othon in 87, and it comes from an implicit calculation. So as you see, as we go out of the domain of the Maxi-Riley equation, we are in a situation where we add pieces to this equation, but we don't have a clear framework. The alternative to all these is to consider the equation for a rigid body, so Euler equation, the conservation the equation for the center of mass and the equation for the rotation of the particle. And this is what we can use in the case of we have even larger particles. Of course, this model increases in the level of complexity and also in the level of intelligibility of this model. This model is for sure accurate, provided that we can compute F and T, but we don't have much physical intuition. It's for this reason that normally we refer continuously to Maxi-Rayleigh equation, because it is something that's on which we can do mathematical reasoning. Then for what concern the numerical and experimental results that I want to provide here as a background, what I would like to mention to start with is a study that I did in 2008. It was a numerical study in which we used the strongly simplified approximation of the Maxi-Rayleigh equation, in which you consider only added mass and Stokes drag. We neglect buoyancy because we consider that the turbulence is so strong that gravity is negligible. This is what we call the beta Stokes model, because the two control parameters are beta and Stokes number, which is tau p over a scale which characterizes the flow. So with this model, we could, in numerical simulation of turbulent flow, we could, for instance, look at the acceleration variance and look how the acceleration variance, which is normally indicated with A0, and it is also called Heisenberg-Yaglom constant. We could see how it varies with beta, which is so modified density ratio, and Stokes. In particular, bubbles, which are here at beta 3, they have much larger acceleration variance, so acceleration intensity than a particle which is neutral, and heavy particle, they have less acceleration. This model also suggests that along this line, along the line beta equal to 1, if we change Stokes, so if we change the size of the particle, the variance remains the same. So this was what the simulation suggested. And with people in Lyon, we tried to check this also experimentally. And in particular, we focused on the case of tracer particles, so particles which are neutral and small, with a size of 1.8 eta, and particles which are much larger. And yeah, eta is a Kolmogorov scale. So 1.8 eta and 15 Kolmogorov scales. We are just outside the inertial, the dissipative range that conventionally is up to 10 Kolmogorov scale. No? So what they saw in the experiment is that if we consider the variance, as I said, in the simulation here, the acceleration variance for tracers and neutral finite size particle is the same. It's 2.5 in these units. A0 is 2.5. Instead, in the case of the experiment, the variance of neutral particles, the neutral particle has much less acceleration than the fluid tracers. Another aspect was the correlation. In the simulation, the correlation, you have to look at this line, the correlation of tracers and neutral particle were the same, while in experiment, neutral particle, they had a correlation which was much longer. So this is the autocorrelation function of the acceleration. The larger is the particle, the smaller are its fluctuations in terms of acceleration, and the longer its correlation time. Looking at the probability density function normalized by the root mean square velocity did not show any remarkable difference between these two cases, neither in the experiment nor in the simulation. Maybe because this was beyond our precision of that time. So this is time. This is time, and this is the autocorrelation function of the one component of the acceleration. So it's a function which starts to 1. Then for a fluid tracers, is here. For a fluid tracers, normally it goes down and then it comes up. And the experiments, could you describe that? Yeah, the experiment was counter-rotating von Karman flow. So that experiment here, it was, I think, a cubic cell, which two propellers which were rotating in opposite direction, and they tracked the trajectory of the particle. Short trajectory because we were interested in the accelerations. Yes, I don't remember precisely, but since these particles are neutrally buoyant, they don't have a big slip velocity. So the Reynolds number of the particle should be very small. For what concerns the shear Reynolds number, well, is small here, but not small here, because this particle is large compared to the typical gradient, to the Kolmogorov scale. So we wanted to do a step more, and the step more was to introduce, a step more in order to understand what was going on and what was the origin of the discrepancy. So we introduced the Faxen corrections. We introduced the Faxen correction in this way. Whenever there is for the term related to added mass, we did a volume average, and for the term related to drag, we did a surface average. This was done not exactly, but it was done in an optimized way. We assumed that the particle had a Gaussian envelope. Since the Fourier transform of the Gaussian is a Gaussian, we could implement this in an efficient way in a spectral simulation. But okay, it's an implementation.
Why is the surface average the relevant one? Like, shouldn't it be more some differences or something between the two sides?
In fact, already in the article of Gatignol and of Maxi, really, there are these corrections, and they were often neglected, but the derivation is there. In particular, it's more clear in Gatignol articles, which use exactly this notation, use surface average for surface-related forces. So that is the good reference. This is just an implementation. Gatignol 1, Gatignol 1983. And this is what we obtain. So I try to explain. Here we have acceleration variance, and here we have the diameter of the particle. There are some experimental data, and then there are the results of the simulation. Instead, in the inset, we have acceleration variance normalized by the acceleration variance of the fluid as a function of the size. So this is the one in the inset is better way to look at the data. And we see that there was a satisfying overlap. There was a reduction of the acceleration variance as we increase the size of the particle. So it seems that Faxen correction were capable to capture this effect shown in the experiment. For what concerns the correlation, and in particular the correlation times, we also saw an increase of the correlation time of the acceleration as a function of the size, although the agreement was not quantitative. And the simulation were suggesting that the flatness of the acceleration was decreasing with the size, while the experiment was suggesting that everything was flat. So we were satisfied for some aspect, but still there were some discrepancies. And what is the way that we try to rationalize the trend that we say here? Essentially, this is the only part of theory I give in this talk, is the coarse, what we call the coarse-grained hypothesis. This hypothesis says that a particle which has a given size d sees turbulence at the scale of the particle and not a smaller scale. So it's averaging all what is below, averaging in space, and as a consequence also averaging in time. So for instance, the acceleration of a particle of size d, we can see as the difference of pressure across a distance, the d divided by d, and this can be related to the increment of velocity squared. And then we use Kolmogorov theory, which says that this scale has L to the 1/3, and then we get this scaling. For the time scale of an eddy in turbulence, we know that it can be estimated as the size of the eddy divided by the typical velocity difference. So the time scale goes like L to the power 2/3. And so the acceleration correlation time will go as d to the power 2/3 by analogy. For what concerns the flatness, so fourth order power divided by the second squared, this is something which involves intermittency correction in turbulence. So in particular, this quantity should go like d to the exponent of order 8 minus 2 times the exponent of order 4, where these are the scaling exponent of the velocity structure function. It should be a quantity negative if there is intermittency, and in particular, less than, it should be of the order minus 0.42 if you use, I think, a Schillebeck model of turbulence. So this is what the coarse-grained turbulent hypothesis gives, and this was the state of the agreement up to that time. We continued with a later work. This was in the von Karman flow at much larger Reynolds number, so 590, 800, up to 1000. And the exponent which were, I mean, the scaling law which we identified was that acceleration variance was going like minus 0.81, which is different from what the coarse-grained hypothesis suggests. Steeper.
R lambda?
R lambda.
The Reynolds you're showing is R lambda?
Yeah, this is R lambda, 590 up to 1000.
How many grid points did you have?
No, this was from the experiment.
Oh, experiment.
Experiment, yes. Simulation comes the slide after. So the temporal correlation was increasing as a power of d and not d to the 2/3. And instead, the agreement on the flatness, but maybe it was accidental, seemed to be compatible with the coarse-grained hypothesis. So we see there are two discrepancies here and here. This is, I think, the most advanced experiment on this property which has been made. And then
was the experiment like modeling homogeneous isotropic? I mean, I guess they took the data right in the middle.
Yes, they took the data right in the middle. This von Karman flow. It's a well-studied setup. In the center is homogeneous isotropic, but it has large scale structure. This is known. Later on, Romain Wolf, one of my collaborators, made a study about the effect of this large scale structure. In that case, he imaged a much larger field of view, and so he could characterize the non-homogeneity in the large scale structure. But here, it was focused right in the center. This is something that you can do if you are interested in acceleration, because the accelerations is correlated over in space and in time of a very narrow region. So the most advanced experiment were this one, and then from 2010, the equipe of Jeremy Beck started to do simulations at much lower Reynolds number, which were fully resolved. So where all the scale of the particle were resolved, and they try to highlight the same type of property. So variance, temporal correlation of the acceleration, and flatness. And the scaling were again different. So there was minus 4/3 instead of minus 2/3. Here it was 2/3, the correlation time, although with very few points, as you can see, and no change in the flatness. After this, there have been other studies with the finite size, fully resolved particle, but not other studies which went into this problem of which are the statistical properties of the accelerations. So this is to set the stage for the problem and the question that motivated us. So first of all, interesting questions are, do finite size particles experience really a coarse-grained acceleration field? Are these scaling laws somehow trustable? Will they be true in a certain Reynolds regime, maybe asymptotically, or is something that we should correct? Or the coupling between the particle and the flow will create its own statistical signal? This is still an open question that we try to address in what I will present immediately later. Another question is, how is this reflected in the particle rotation? So the quartz grain hypothesis says that the angular velocity, which is dimensioning 1 over time, should scale like d to the power minus 2/3. This is something that we can verify now that we can simulate and also track experimentally particle. And in particular, when we discuss about rotations, it makes sense to also look to anisotropic particles. So when the particles are not spherical, they are much more interesting. First of all, we can track their rotation easily, especially in the experiment. They can have preferential alignment with certain flow structure. And so the question is, when the particle is very large, will it align with preferentially still, or will it randomize its orientations? And yes, the last question, a bit philosophical, is what do we learn of turbulence when we look to this moving particle? Is it possible? So the focus is not only on turbulence, but is also on what is the flow. The focus is not only on particle, but it is what is the flow that create this effect. So we try to tackle these questions by means of a new numerical simulation similar to the one of Jeremy and Holger Hohmann, in which we fully resolve Navier-Stokes, we resolve Newton-Euler equation for the particles, and we implement no-slip boundary condition at the fluid-particle interface. So this was done in collaboration with my colleague in China, Chao Sun, and the PhD student who worked on this, Linfeng Zhang. It was during the COVID time. Linfeng started this PhD as an experimentalist, then he couldn't go to the lab. So he implemented in the code that I have developed, he implemented this immerse boundary and tracking strategy by using methods which are pretty standard. In particular, our reference was this article by Suzuki and Inamuro on computational fluids. And what we simulate, so the parameter space in our simulation has been this. First of all, we study 4 types of particles. Axisymmetric particles, which are either disks characterized by an aspect ratio of 1/2 length over diameter, spheres, or rods with aspect ratio 4. Another characteristic parameter is the volume equivalent diameter, which is diameter to alpha to the power of 1/3. The Reynolds number, we simulated 2 Reynolds number, this and the one simulated by Jeremy, so 32. This is length, this is diameter, these are the equivalent radius, and these points represent the type of particles that we have simulated. Yes? And we were considering single spheres, so non-interacting. But these simulations are quite heavy because every time you want to perform a simulation with a different type of particle, you have to run a different simulation. So in some cases, we put multiple particles in them, and we were very careful to remove from the analysis all the cases in which they come close to each other. But most of the simulations were done with a single particle, like in the case of Jeremy. Yes, but these particles are quite big, so you need at least 16 points. So the minimal size of the particle is 16 grid points, and the Kolmogorov size, Kolmogorov scale is 1.5 grid points. So these particles are quite big. We could satisfy the boundary conditions at the price of having large particles. We are in a favorable situation here because these particles they are not subjected to gravity, so they don't fall. Their slip velocity is very, very mild. So the boundary layers around them is large. If you include gravity, it becomes critical, and you have to increase the resolution. So since we do simulations, we have some freedom. We can simulate real particles, particles which have real boundary conditions, but also invent other type of particles. For instance, we can consider volume averages. So we draw an ellipsoid in the fluid, and then we compute the acceleration of the fluid, which is there, and also the angular velocity, so the vorticity. This will be useful. We thought it was useful to introduce this auxiliary particle in order to understand then what we measure. Then we introduced the virtual particles, so particles which move exactly as the others, but for which we disabled the immersed boundary, so we disabled the boundary conditions. So it's just a region of flow which moves, and then it appeared to arrive in another position. The fluid which is there inside that region is different from the fluid that was before, because the boundary conditions are not implemented.
So it's something which moves with the same average velocity, same kind of rotation.
Yes, I think we can imagine this like a sort of cage, like a cage with a lot of holes, which moves like a normal particle, but for which there are no boundaries.
The volume contain, let's say, the identity of this. The volume average one, the bottom right.
The volume average. So simply we draw a surface, and then we compute what is the acceleration inside.
How do you keep that surface the same over time?
No, we don't keep. It's just really a volume average. Imagine that you have your velocity field. You draw in it an ellipse, and you average the acceleration over there. And you say this is the acceleration that we would have in a volume average.
But is this thing moving? Like,
no.
Is that boundary moving?
No, this is not moving. These are fixed, and these instead are moving. The virtual particles are moving.
So all of these comparisons are possible because they're neutrally buoyant.
Because they are neutrally buoyant, yes.
If
and
they were not, then a virtual particle will do something completely different than a real particle.
We can invent these virtual particles also if they are non-neutrally buoyant. But if they are non-neutrally buoyant, I think
There will be some other body force, so it will become a different problem.
Yes. So here essentially, you see, our code is made by three pieces: Navier-Stokes, Newton-Euler equation, and immersed boundary. And we turn on and off these elements. Then also it is useful to introduce zero inertia particles, so Jeffrey fluid tracer particles which follow the fluid and they move like if they were Jeffrey, small ellipsoids, to compare what is the effect of the finite size. And there are also these two exotic families on which I will tell you later, which are real particle fixed at the location. So particles can only rotate, but they are always fixed, and virtual particles which are fixed. So this will be useful to interpret the data later on. So let's see the result. First of all, we play, in order to validate the simulation, among the many validation, we played with the spherical particle, and we compare the results with the result of Oman and Beck. In particular, here you see the acceleration variance as a function of the size. Our dots are the solid ones, the solid symbols, and the empty one are the one from this work. And we have compatible results, I would say. These are totally different numerical methods. My code is Lattice-Boltzmann. That one was a spectral code. Resolution are different. The only thing which is equal is the physical parameter that we put in it. And we were satisfied to see this, to see decrease of the acceleration variance as we increase the size, increase of the correlation time, and a reduction of the flatness, mild, I mean, comparable to the what that Jeremy said. We did this comparison, and we did a comparison also at larger Reynolds number, the largest that we could simulate, and we have the same quantity, while the empty symbols are the experiment by Romain Volk at much larger Reynolds number. As you see, for instance, for a variance, here we have -4/3. Then when we go to Reynolds number 120, we have -1. And at Reynolds lambda 1000, we have -2/3. So all these points to the fact that probably the quartz grained hypothesis is true, but there is a strong Reynolds dependence. We will be able to reply to this question when we will be able to do simulation at Reynolds 1000 with real particles. The same trends are observed. The flatness is surprisingly agreeing with the one in the experiment. Similar trends are seen for the correlation. So we are satisfied with this spherical particle, and now I will talk.
Flatness and Jeremy's flatness were different.
Yes. So these are different. Flatness, you know, is fourth order moment, is something that you need a lot of statistics. If we we should put error bars in this type of graph. We should at least divide our data set into parts and see what is the difference. It might be that they are compatible, maybe not. The same for this case. So now I would like to talk about spheroids, where we try to do the same type of measurements. And in particular, here you see the acceleration variance normalized by the acceleration variance of fluid tracers for real particle, solid, and for volume averages. And you see that scaling-wise, they behave the same, even if there is an offset in their amplitude. So this suggests that, yes, the quartz-grain hypothesis scaling-wise seems to be correct, but we do not capture its amplitude. For this reason, we tried to compare real particle with virtual particle, and we get a much better overlap. What is the difference between volume average and virtual particle? Volume average are circle or ellipsoid that we draw in the flow. Instead, virtual particle are particle which moves in the flow. They can have a sort of preferential sampling. So this say that the scaling properties of acceleration, they are due to volume averaging, but with the inclusion of preferential sampling of virtual particle, we also get quantitatively correct the same result.
Is it because that thing is Eulerian and this is Lagrangian, it's following?
Yes, yes. This is Eulerian. It is fixed. We put an array of ellipsoids. And so we are sampling the space uniformly. Instead, here we are sampling the flow.
So your hypothesis somehow is for Eulerian things because you're just going by Kolmogorov scaling.
Yes.
You're not following the same thing in time.
Exactly. So the quartz-grained hypothesis should be extended to the Lagrangian frame in order to have quantitative agreement. Otherwise, you have a qualitative agreement. And another thing I want to yes. So but I will come back maybe on a point related to this. So better overlap with the virtual particle. Another thing that we could analyze is the decomposition of acceleration of the particle in an axial component and in a transverse component. So in particular, we looked at axial acceleration divided by transverse acceleration. And this is what we obtain for a real particle. So this is the aspect ratio. One is a sphere. So the ratio between axial and transverse is 0.5. And then what we find is that for a rod-like particle, we have more axial acceleration no, this is, we have more transfer acceleration than for disk. So this is a bit counterintuitive.
The Turbulent spheroid is moving along its long axis. That's what you're saying.
Yes. So the point is that you have a long object, and this long object, instead of having faster acceleration, larger acceleration, it is in this direction. So this is a bit counterintuitive.
Yes, because the added mass is more.
The added mass is more, and also the drag is accelerating more in the direction where you have more drag.
That's like active particles do the opposite, right? Like they follow their nose.
Active particle do the opposite. Do the opposite.
So.
Yes. So we try to understand this, and to understand this, what we did is that we put virtual volume averages, and volume average are 0.5. So this is an effect due to some preferential orientation. And then we put virtual particles. So virtual particles behave as real particles. And then surprisingly, we put Jeffrey tracers, so inertialess particles, and they also behave the same. So the question is, what is the explanation of this? Why these particles are all having this repartition of acceleration? And
it's also size independent, right?
And is also size independent. So the reply that we had, the qualitative explanation is this for us, is that in experiments, for instance, this experiment by Lieberson, they showed that this is the PDF of the cosinus between the acceleration and the vorticity. It is peaked in 0. So this means that there is a preferential, the acceleration in a fluid is preferentially orthogonal to the vorticity. And then from the work of Luca Biferale, we know that there are vortex filaments in turbulence. So you have, in vortex filament, you have this vorticity, and along the vortex, and then you have strong centripetal acceleration. So this is the reason why in turbulence, vorticity is often perpendicular to acceleration, because you have strong acceleration.
Is this because the particle is as big as the vortex?
So these are measurements for fluid tracers. So this is Lagrangian trajectory. The Lagrangian trajectory.
Just fluid tracers.
Yes, these are fluid tracers. But I'm coming to the explanation of what we have seen in the slide before, to understand why elongated particle, they have larger transverse acceleration as compared to longitudinal acceleration. And the explanation is this.
Question, but why does a neutral object have centripetal acceleration?
Also, well, centripetal acceleration because there is no mass. This is, you say, but it's simply a decomposition. Okay. It's simply a decomposition. We call it centripetal because it is in a vortex, but in fact, this is almost total the acceleration of this. So essentially, if you are doing a circulating motions, you will have an acceleration which is pointing toward the center. Then Alain Poumire and Wilkinson, they showed in this article that elongated particles, they align with vorticity, okay? So then what, and while on the other hand, in this article, Greg Vaught showed that disks do the other thing. So this shows that elongated particle will have larger transverse acceleration and as compared to the axial acceleration, because this particle, they go in a vortex, they are big, they cannot stay in a vortex, or they will not be always on the axis of the vortex, so they have a lot of acceleration in the transverse direction. And the opposite is happening for disks. So this is the explanation of this strange trend that we saw here. The vortex, yes, this is something, this is a question which is it's difficult to reply. So these vortex here, they have typically the size of Kolmogorov scale. These are really the smallest vortex that you can have in turbulence. What is outside these? We don't know. So the question is that how will this vortex decay? I don't know. The fact that we see the same behavior for finite size particles who have a radius, a diameter of 15 Kolmogorov scale, it means that this vortex, their intensity extends also laterally. So this is the question I made in blue in my previous slides. What we learn about turbulence? We learn that there are structures, and these structures are important even for very large particles. And they provide a statistical signature on the acceleration. Yeah. So this is the trajectory of a fluid tracer. So if you look at the fluid tracer, it will have this type of trajectory in turbulence. It will be sometimes trapped in a vortex. And while he is in this region, he will have an acceleration which is pointing perpendicular to omega. Okay. Now, if this is not a fluid, is not a fluid tracer, but is a Jeffrey tracers, what will happen? That the center of mass will do the same trajectory. And that the vector P will orient preferentially along omega. So a Jeffrey tracers, a particle which is without inertia but with a shape, will experience an acceleration which is perpendicular to P. This is clear, and it happens for sub-Kolmogorov or no inertia particles. Now, for the particles which are large, what I'm saying is that probably what is happening is the same thing, because the repartition of axial and transverse accelerations appears to be the same. This is. So it means also that the effect of having a size for a neutrally buoyant particle is not major. It basically behaves, apart from the filtering it behaves more or less as a fluid tracer. The situation will be very different for what concerns rotation. Is it more clear? Yeah. Okay. So in conclusion,
nice way of doing it, like looking at the virtual particle and the volume average. It's really nice.
Thank you. So in conclusion, on acceleration, the side dependence explanation is explained by fluid acceleration volume averages, but the amplitude is better accounted if you use volume, if you use virtual particles. So there is an effect of preferential sampling. And it is important, we have learned that fluid structure are important in the description of this phenomenon. Now, the question is that what happens for rotation? And we will see that the situation is quite different. So for rotation, we have real particles and volume averages. Real particles are here, sphere. They scale according to the prediction of the quartz grain, -4/3. So it should be this to the square. It's quite clear for sphere. There is a big offset with volume averages, and this offset remains when we consider virtual particle. So there is not, we cannot overlap. It's not an effect just of preferential sampling and so on. No overlap, so this is different from the acceleration. If we consider the transverse rotation, so the tumbling rate, this type of movement, compared to the spinning movement, and in particular, we consider its ratio, we can expect two things. The quartz grain prediction says that spinning will go like diameter to the minus 4/3. And the tumbling will go like length to the minus 4/3. And then when you take the ratio spinning over tumbling, you will have something which is independent of the size of the particle, going like alpha to the 4/3. This is not the only prediction that you can make. Another prediction is that you can think that these particles, they will be randomly oriented with respect to the direction of velocity gradients in turbulence. So if you work out with this hypothesis, you will end up with a prediction which says that still you do not depend on the size of the particle, but the function will be symmetrical with respect to the case of a sphere. So now, which one of these two hypotheses is valid? Of this prediction is valid. So this is the point. You should remark that both these predictions, they say that there is no size dependence. So this is spinning rate variance over tumbling rate variance as a function of aspect ratio. It is a function which is increasing. So it means that rod-like particle, they spin more than tumble, and the disks, they do the opposite. Here there are two data sets from the simulation by Byron et al. So a larger Reynolds number. It's a quantity which are very weak Reynolds dependence. And these are our simulation for fluid tracers. Now, when we put the randomly oriented prediction, we see that this is not satisfying. So it's very far. And the reason for this is that there are preferential orientations. As we were saying, the particle, which are elongated, align with vorticity, and these create these patterns. So
Is this random?
The initial conditions are random.
So what do you mean by randomly oriented?
Randomly oriented, I mean that the particle, I mean that there is no correlation between the vector P and any component of the gradient of the velocity. Okay, so you can, when you take averages, you can separate the two terms as independent variables. Okay,
That's a consequence of the dynamics of Lima. That's not something
that is a prediction. But you could think that you know that this happened. For instance, there are no correlation with develops, the flow is changing, but in fact, it's not like that. The particle has the time to adapt to the flow, and what we see is that tiny tracers, they, for instance, if they are rod-like, they spin a lot, and this is because they go into vortices, the same mechanism we were saying, and they rotate a lot and tumble much less. Now, what happens when we have a real particle? This is what happens, is that we have, this is the size of the particle, we have a strong size dependence, okay? And now the point is that how do we explain this? And so this was challenging. I don't know if we have a proper explanation. We have some hints.
So Jeffrey tracers don't move with the particle, or do they? They rotate like a particle.
Jeffrey tracers are, they have an equation which is the derivative of its position is equal to the velocity of the fluid, so the equation for a tracer, and then they have a separate equation for the orientation. P dot is equal to Jeffrey terms, okay? So I mean that for Jeffrey tracers, they are tracers both for the center of mass and for their orientation.
So what's happening is this, just to understand, the size is going down more.
So what is happening? Is happening, for instance, that if you have a rod-like particles, the same thing is happening for all the particles when we increase the size. So you increase the size of a rod, and it will progressively tumble more than spin. Tumble more with respect to the spinning. The same for a disk. This is less than 1. This for the sphere, of course, everything is equal to 1. the sphere will not have any effect. You increase the size, they continue not to feel any preferential orientation.
Oh, your color bar, sorry, yeah, it increases in the downward direction.
It goes down. Okay. So how to explain these? This is a very robust observation from the simulation. So as we increase the size of the particle, we have more tumbling and less spinning. This seems to scale like spinning over tumbling. The variances go like diameter to the minus 0.6. If we use volume averages of virtual particle, we do not explain these trends. In particular, if we use volume averages, since these volume averages, they are drawn and never change, volume average follows the minus 1/3 prediction, okay? The quartz grain prediction. Instead, virtual particles, they seem to adapt to the randomly oriented prediction. So these two models, these two type of particles, they do not help us in describing what is happening. And it is for this reason that we thought, okay, let's try particles which have real boundaries but are fixed in position. And let's try then particles which are virtual, they don't have boundary, but they can only rotate and they are fixed in position. So real particle fixed location, it means virtual particle at fixed location. And what we see is that for the case of real particle at fixed location, we get scaling and quantitative agreement. And also we have, when we look at spinning over tumbling, we have a decrease of spinning as compared to tumbling, while for virtual particle, we do not get this. So what is the conclusion? The conclusion is that the particles which are showing this behavior, they are particles which are for which we have implemented the interface boundary conditions. So what I call a real particle, they are particles for which we have implemented immerse boundary. The velocity goes to 0 at the particle. So this means that there are boundary layers. So boundary layers seems to be crucial here. So this is the hypothesis. This behavior is a behavior which is not due to averaging, but is due to boundary layer. It makes sense that when you have an object which is rotating, that boundary layer at some point will become important. And yes, this is basically the end. We try, if we estimate what will be the Reynolds number of this particle, essentially, you can estimate that the Reynolds number of the particle is of the order 100. It goes like the diameter of the particle divided by the Taylor scale times the Reynolds number. And we see from visualization which we have boundary layers, which have also been studied in these articles.
Simulations, you didn't make any assumption about the Reynolds, right?
No, we did not make any assumption. We just looked that the boundary layer is well resolved around the particle, and that the that the fluid velocity goes to 0 at the particle interface. So
did you need adaptive gridding?
No, we did not use adaptive gridding, but it is needed for particles which have a density different from the one of the fluid. So Lim Feng has continued these simulations. He's now studying bubbles, and he has implemented the grid refinement. Because the Reynolds number of the particle is quite small, and so the thickness of the boundary layer is large. Instead, if you have a bubble, it will go up, and you will have immediately very large Reynolds number. The slip velocity U minus V here is essentially, you can assume that V is of the same order of U. No? So this it's of the order of U prime, the slip velocity. It cannot be larger than U prime. Instead, if you have a particle which is subject to gravity, this term will be of the order of at least of the sedimenting velocity. So it will be, can be much larger.
Gravity.
Yes. Yes. Then I don't think these are the most well-resolved simulations that there are on the market, but all what the tests that we made were compatible with previous results, so we were confident about it. And we did a last measurement. So we saved the velocity field around the particle, and then we decomposed it in rotational and strain parts. And then we plot the rotational part divided by the dissipation, so the strain, and we looked what is happening around the particle. And we see that there is an increase in strain rate as compared to vorticity. So if there is an increase in S with respect to omega, this means that the particle will have the tendency to tumble more, which is what is happening. So it's a qualitative explanation of the trend that we have seen. More studies are needed to get a quantitative understanding. So in conclusion, for rotation, is not the same story as acceleration. Size dependence can be explained in terms of volume average, but not its amplitude, independently of the volume average, even if you use virtual particles. And the boundary layers, so the two-way coupling between the particle and the fluid, which decrease the spinning with respect to tumbling, is an effect to be kept into account.
And it as like this particle wants to spin. Suppose it starts spinning very fast, then the boundary layer is going to oppose that. The boundary layer is going to dissipate the spin.
Yeah, it's possible. Yeah. Yes, it makes sense to me. Yeah. Because if the particle moves with the flow, there will be no boundary layer. But if the particles start to rotate, boundary layer will be created. So, yes. So in conclusion, we need more experimental and verification and numerical simulation. There are not, so there is one experiment that came out recently by a group in Marseille, in which they explore this ratio of spinning over tumbling for particles, and their data are here. There is a trend in decrease, but not very clear. I mean, you see, the data connected with the line are our data, and these are their cloud of points, but the aspect ratio are different. Reynolds number is different. It is difficult to say. And even if this is confirmed, then we have still to find an explanation. Well, okay, that's it. Yes, no, because the acceleration gives us immediate information about the force. So measuring the acceleration is like measuring the force. So this is a way to, most direct way to understand what are the physical effects which matters. For instance, which force should we consider? If we were obtaining totally different results, then we would have to introduce, for instance, history force or other type of force to get a quantitative agreement. It appears that in turbulence, these models, I mean, the point-like model already with two forces described very, very well what we see with the level of accuracy that we have at the moment. So for that reason, acceleration was a studied, well-studied observables. And the other thing is that it is easier experimentally because you just need not very long trajectory to compute accelerations. You just differentiate very short tracks and you get the acceleration. You can image this in a very concentrated area of your setup. Yes, so here what we did is that we saved the velocity field around the particle while the particle was moving. And then we computed the velocity gradient of the velocity field in that region. And then from the velocity gradient, we computed vorticity squared divided by 4, divided by S double contracted. So this quantity, I think in homogeneous isotopic turbulence should be 1 everywhere. No, should be 1, its global average should be 1. But what we see is that close to a particle boundaries, it becomes larger than 1. So this means that around the particle, omega, the rotational part of the flow is less important than the shear part. Okay? No, it should be the opposite. So very close, yes, it goes upper than 1, and then there is a region, this wide region where it is below. So this region would influence the behavior of this quantity. We did not do this with the particle size. We tried with we did not investigate this systematically for all the particle size. We just wanted to see what happens around the particle. There is a very thin shell where vorticity is more important, and then there is a much wider region in which shear is important. And then, you know, since in Jeffrey equation, you have, so Jeffrey equation, where is it? This part is responsible for tumbling. So if this part become in the flow, if S in the flow, the rate of strain becomes more important than the rate of rotations, tumbling will dominate. But this is just a qualitative speculation. We don't have any. What is solid is the fact that we observe this phenomenon. As the particle is increased, spinning becomes more important than tumbling. And this is not predicted by the coarse-grained hypothesis. But it can be explained, as Rama was saying, by the fact that when a particle rotates, create a boundary layer. So this is intimately a two-way coupled problem.
One is, okay, so we start with this one. So with the larger ones, larger sizes are more prone to spinning. So could it be because, let's say isotropy or similarity is broken at the small scales only. So once the objects are large enough, then most of the tumbling probably comes from smaller size vortices, which are getting averaged out.
Yes, but in that case, if this was true, I would expect an isotropization. So I would expect that a particle, when it has a very large size, its spinning over tumbling will go like what is happening for a sphere. So that we will approach 0.5. This is what I meant as for isotropization. Instead, here it seems systematic for this 3 aspect ratio that we investigated that we go towards a state where we tumble much more than spinning.
Right. I mean, of course, this cannot average out the thing in the other direction because it's a long one.
Yes.
It can only average out in 1 or 2 directions.
Yes.
So like the elongated one will not average out in 2 directions. This one will not average out in 1 direction. So maybe that has some permanent effect. Yes,
yes. There are also in this article by Hohemke, Gauthier-Verhil, they suggest the fact that we cannot use coarse-grained hypotheses when the particles are so large because we have to keep into account that there is a certain spatial correlation of this quantity. So you cannot assume that if your the spinning of your particle will always go as the diameter at a certain power. At some point, you will reach a state where It's not correlated.
And one thing about the real particle and the real particle fixed location. You had
Yes.
So first of all, yeah, it's really interesting to use all these kinds of particles. Some of them are new for me, at least. I was curious. Can you go to that figure?
Yes. So I think it's later. Yes.
This one. They basically are very close, right? The results?
Yeah, these are very close. I mean, we try to put error bars there, one on the top of the other, you see.
So that means that this is what then an Eulerian effect or something? Because I mean, the fixed location is not moving anymore. So it becomes, I don't know.
So for me, this means that particles which are fixed, they are rotating similarly to particles which are moving. So it means that
It's some ergodic sort of thing, is it? Like, doesn't need to move anymore, but the statistics are similar.
yeah, so it means that the preferential sampling in this case is negligible effect. What is important is the boundary layer that you create around the particle.
How do you even define P for a sphere?
P for a sphere. So if you have a sphere, you can always draw a dot on a sphere and say that P is the vector which starts from the center of the sphere, pass through this dot.
Okay, so just a randomly chosen term.
Just a randomly chosen dot.
That was a really nice talk. So let's thank everyone.
Thank you.